Okay, so so you are alone so far. Let us wait for others. Okay, we have two people. Anyway, let us start. And I have just uploaded this yesterday's material to Google Classroom. Uh, so refrigerator and coefficient of performance and the video. Yesterday's video, recorded video, have been uploaded to Google Classroom. Okay. Okay, so today's topic is okay. I have to share with you what is the topic today. It is called absolute or thermodynamic scale of temperature. Where is it? Here, this one, absolute or thermodynamic scale of temperature. Okay, so but still you are two people. I wish there had been more people and we could discuss. Anyway, let us start. Okay, so this is the topic. I think this is the last topic from Unit 1, and then we finish Unit 1. Okay, after this, we can go to, I'll see, maybe we can go to, well, I can go to Unit 2. It's better to go stepwise. Okay, so let us see if we can finish this topic today. With that, we are done with Unit 1. Okay. Okay, so thermodynamic scale of temperature. Okay, so let us learn what it is. A bit long topic. Mathematical derivation is long, but it is not very difficult. Okay, so this is actually an application of second law of thermodynamics. So second law of thermodynamics, in your syllabus we have learned about the second law of thermodynamics. Then we have learned about heat engines. We have learned about the Carnot cycle, Carnot's engine, work done during a Carnot cycle, then efficiency of a Carnot's engine. Then we have learned yesterday we have learned about refrigerator, and refrigerators are nothing but heat engines which act in the reverse direction. Okay, so refrigerators are also like an application of your second law of thermodynamics. Okay, and this scale of temperature, this thermodynamic or absolute scale of temperature, this is also an application of second law of thermodynamics. So in your syllabus, you will find that the application of second law of thermodynamics is also given. Okay. Okay. So thermodynamic temperature scale. Okay. This is what we are going to learn. So I am writing the note. I have written half. The rest half I can write and I will upload as soon as possible. Okay. Okay. In the investigation of measurement of temperature, all skills depend on properties of particular substance. Okay. Like expansion of mercury, change in resistance of platinum, etc., with rise in temperature. The nature of the substance and the property used for finding the temperature influence the value of the temperature measured. So temperature measures are arbitrary and show a remarkable degree of disagreement. Okay, so there are some certain physical phenomenon when the temperature increase or rise or temperature change, they depend on the substance. Okay, like expansion of mercury. Okay, how much mercury will expand with respect to heat, that will depend on the nature of mercury. Similarly, resistance change in platinum, no, this platinum resistance thermometer. So how much, what will be the observed resistance change in such PRT or platinum resistance thermometer? That will also depend on the material. Okay. So nature of substance and property. Okay, substances nature and property for finding temperature influence the value of temperature measure. So this is not always true, or there may be certain disagreements. Why disagreements? If temperature or temperature related properties of a substance depend on the temperature itself. Okay. So to address that problem or disagreement, because mercury will expand differently, iron will expand differently for same difference in temperature. Suppose mercury you initially put at 30 degrees Celsius, then you heat it up to suppose 70 degrees Celsius. Okay. So in this 40-degree rise in temperature, mercury will expand differently. Similarly, iron will also show different behavior if iron is heated from suppose within the same temperature 30 to 70 degrees Celsius. Okay. Yeah, so that's a like no, we cannot establish a common connection in these two processes. So that's a kind of no deficiency, or that's a problem. So what this person did, Lord Kelvin. So we have learned about this Kelvin Planck statement of second law of thermodynamics. So it is the same person, Kelvin. Okay. Okay, let me just drink some water. Okay, so what Lord Kelvin did from a study of efficiency of a reversible heat engine and application of second law of thermodynamics, obtained a new temperature scale. Okay, Kelvin found a new scale of temperature which is independent of the properties of particular substance. Okay, so the new scale of temperature, Lord Kelvin, with this no, from the reversible heat engine and with application of second law of thermodynamics. So when he was studying these things, so he found a new temperature scale. Okay, and which depends on the properties, which does not depend on, okay, which is independent or which does not depend on the properties of that particular substance. Okay, and dependent on particular substance. Okay, and therefore non-arbitrary. Non-arbitrary means it is not different for different substances. Okay, it is same if we are using, so you recall the Carnot cycle. So on what things the efficiency of a Carnot engine depend? It depends on only two things. The two things are what is the temperature of the source and what is the temperature of the sink, or how much heat you are getting from the source and how much heat you are rejecting to the sink. So only on that thing the efficiency of the Carnot cycle depends. Okay, so you see the efficiency thing of a heat engine, it is not dependent on the nature of the material. The material may be anything, the working substance may be anything, but irrespective of the working substance, the efficiency will depend only on the initial, only on the temperature of the source and that of the sink. Okay. So and therefore they are non-arbitrary. Non-arbitrary, arbitrary means they may have any value or they may have like no fixed definition, but non-arbitrary means they are fixed. Okay, they cannot just vary from substance to substance or material to material. Okay, so with this new temperature scale which Lord Kelvin found, It is called absolute work or Kelvin or thermodynamic scale of temperature. So several names: absolute scale of temperature or thermodynamic scale of temperature. Okay, also known as Kelvin scale of temperature. But I think you don't have to go for all these things. In your syllabus, it is given absolute or thermodynamic scale of temperature. Okay. So that is what the Lord Kelvin, this person, I think if I remember well, he is a British scientist, he found. Okay, the efficiency of all reversible Carnot engines. Okay, just now I have mentioned the efficiency of all reversible Carnot engine working between two temperatures is a function of two temperatures. If Q1 is the quantity of heat absorbed at a high temperature theta 1 and Q2 is the quantity of heat given at a low temperature theta 2, where theta 1 and theta 2 are the temperatures measured on an arbitrary scale, then the efficiency can be written as like this. Okay. So this thing we know, we have already learned from the concept of heat engine and also from the concept of uh, what is his name? Uh, yeah, I forgot. Carnot cycle. Yeah. So what we learned in a Carnot cycle, so if Q1 is the quantity of heat that we also assume taken from the source or at a high temperature maintained at theta 1, and Q2 is the quantity of heat at a lower temperature theta 2, and theta 1 and theta 2 are like temperatures measured on any arbitrary scale. Any arbitrary scale means maybe theta 1 may be in degrees Celsius or theta 1 may be in Kelvin or even Fahrenheit. Similarly, theta 2 may be in Kelvin, in degrees Celsius, in Fahrenheit, in whatever. That is why arbitrary scale. Scale means it's like Celsius, degree Celsius, or Kelvin, or Fahrenheit, like that. Okay. In that case, what is the efficiency? Efficiency is this expression we already know. Okay. So okay, let me annotate. So that you annotation is required so that you understand this. Just give me a moment. Okay. So efficiency is what color is this color? Let me change the color. Okay. So efficiency is this one equal to it's Q1 minus Q2 by Q1. Oh, by Q1. Okay. Now efficiency is also like this theta. Okay. This time the source is assumed to be at temperature theta 1 and the sink is assumed to be at temperature theta 2. So theta 1 minus theta 2 equal to theta 1 minus theta 2 divided by theta 1. It is I earlier wrote this as theta 2, but it is actually theta 1. Okay. So this is how we can write the efficiency of Carnot cycle or Carnot engine. And therefore this eta the efficiency is a function of theta 1 and theta 2. Okay. Therefore eta, so instead of writing them in number, let us write that it is a function of f is a function of theta 1 comma theta 2. In other words, okay, this is theta. Okay, don't get confused. This is theta. Okay, this is theta. I'm finding it difficult to write here, but it's theta. Okay, so yeah, so this efficiency of this heat engine is a function of theta 1 and theta 2, the temperatures at which the source and the sink are maintained. Okay, so that is why it is written like this. Okay, for this reason. So this refers to this. Here they have like skipped one line, one part. We're writing this. Therefore, this one we can write q1 by q1 is 1 minus q2 divided by q1 is a function of f theta 1 theta 2. Okay. Or how you can write q1 divided by q2. Q1 divided by q2 is like they have written to be. So you have understood how this is coming. So q2 by q1 is 1 minus f theta 1 theta 2. Therefore, q1 divided by q2 is equal to 1 divided by small f theta 1 minus theta 2. Okay. Okay. Let me write. Okay. Let me write so that you don't get confused. So anyway, I'm first writing q2 divided by q1 is 1 minus f theta 1 theta 2. Okay, but here we are writing it as q1 by q2. So what is q1 and q1 divided by q2? From here just reverse this. Okay, if you reverse this, okay, let me write because I think we have enough time. Okay, do you think we have enough time? What is your opinion? So you have no opinion about how much time we have? Okay. So this is more or less going to be the last topic of Unit 1, and then maybe one or two classes I will do numericals. Okay. So q1 by q2 is 1 divided by f theta 1. So handwriting is very bad because it's difficult to write actually. This is this is 1. So it's so difficult to write 1. This is nothing but 1. q1 by q2, 1 divided by 1 minus f theta 1 theta 2. Okay. Okay. Yeah. So you have understood this. But now 1 divided by 1 minus small f theta 1 theta 2, they have taken to be equal to capital F theta 1 theta 2. I mean, it is another function which is again dependent on these two temperatures theta 1 and theta 2. So that this capital F theta 1 theta 2 is equal to 1 divided by 1 minus small f theta 1 theta 2. You have understood up to this, up to equation 1. You have understood. This is equation 1. You have understood or not? It's simple, just
Yes, sir.
numerical. Yeah, just numerical steps. If you have understood up to equation 1, then for equation for the next case, what is the next case? If similarly we have another reversible heat engine working between temperatures theta 2 and theta 3. Okay, earlier we assumed that the temperatures were theta 1 and theta 2. Now we have another reversible heat engine which is assumed to be working between temperatures theta 2 and theta 3. In that case, what we can write, you see q1 by q2 is f theta 1. F means a function of theta 1 and theta 2. Therefore, q2 divided by q3 is a function of theta 2 and theta 3. Okay. Have you understood this? So we don't have to do all these steps now because once we have got this, equation 1, so for any reversible heat engine operating between the two temperatures theta 2 and theta 3, we get this expression, okay, which is a function of theta 2 theta 3. Fine. Okay, so after this you get you multiply equations 1 and 2 and see what happens. Okay, so multiplying equations 1 and 2, we get so q1 by q2, q2 by q3. Okay, q2 gets cancelled, q1 by q3, which will be nothing but equal to f theta 1 theta 2 multiplied by f theta 2 theta 3. Okay, that is equation number 3. Okay, have you understood this? Just nothing but just multiply equations 1 and 2. So Q2 is in the denominator here, numerator, so they will get cancelled. We will be left with Q1 by Q3. Okay. Uh, Now let's see what's written next. Now if we have a reversible heat engine working between temperatures theta 1 and theta 3, okay, reversible heat engine. So earlier we had reversible heat engine working between temperatures theta 1 and theta 2. Then we had considered another reversible heat engine working between temperatures theta 2 and theta 3. Now that we have the expressions Q1 by Q3, okay, Q1 by Q3. So if you compare equation 3 with equation either with equation 2 or equation 1, then what we'll get. Now say, okay, so let us see this paragraph what is written here. So now if we have a reversible heat engine working between temperatures theta 1 and theta 3, such that it absorbs a quantity of heat Q1 at temperature theta 1 and rejects a quantity of heat Q3 at temperature of theta 3, then Q1 by Q3 in the same line, okay, on the same line equivalently we can write Q1 by Q3. Why we are writing Q1 by Q3? Because we already got in equation 3, after multiplying equations 1 and 2, we got an expression Q1 by Q3. Okay. So Q1 by Q3 will be a function of theta 1, theta 3. Because if Q1 by Q2 is a function of theta 1 by theta 2, and Q2 by Q3 is a function of theta 2 and theta 3, therefore Q1 by Q3 is a function of theta 1 and theta 3. Okay, so you have understood this, or you don't even have to understand. Just if you are getting some you are getting an expression like this, Q1 Q2 theta 1 theta 2 Q2 Q3 theta 2 theta 3, then it is normal. Okay, yeah, okay. Okay, so I have to remove the annotation because I have to go to the next page. Not next page, but next segment. Okay, so Q1 divided by Q3 has been found to be a function of, okay, I can again start annotating here. Oh, again the fat one. I like. Yeah, if Q1 by Q3 is a function of theta 1 and theta 3. Comparing equations 3 and 4. Okay, in equation 3 what we got. Okay, so okay, let me remove the annotation. Yeah, equation 3 and 4. So what did we get in equation 3? In equation 3 we got Q1 by Q3 is a multiplication of f theta 1 theta 2 and f theta 2 theta 3. Here what we are getting, Q1 by Q3. We have the left hand side of both the equations being the same, the right hand sides will also be equal, and Q1 by Q3 will be nothing but a function of theta 1 and theta 3. Okay, therefore from equations 3 and 4 we get f function theta 1 theta 3, this quantity will be equal to this quantity. Okay, so this quantity is equal to this quantity. Why? Because these two quantities are equal. So that is what is written now. F theta 1 theta 3 is equal to f theta 1 theta 2 multiplied by f okay, there is a printing mistake here. This should have been theta 2. Okay, so here it was written to be theta 1, but it will not be theta 1, it will be theta 2. So f theta 1 theta 3 is equal to f theta 1 theta 2 multiplied by f theta 2 theta 3. So let me check what did I write in your note. Okay, I have also written to be f theta 1, which is wrong. Okay, I have corrected it in your note also. So f theta 2 theta 3. Okay, up to equation 5, I hope it is clear. Then in equation 5, we find that theta 2 is not present on the left hand side. Okay, theta 2 is not present on the left hand side here, but it is present in both the factors on right hand side. So it is it is present here and here, but it is theta 2 is not present here. Okay, now no theta 2 quantity here, but theta 2 as a quantity appears in the first expression and here in the second expression. Therefore, the form f theta 1 theta 2 must be given by, yeah. So if the quantity theta 2 is vanishing, you see the theta 2 is vanishing in the final multiplication. Therefore, f theta 1 theta 2, this quantity, it can be written as a quantity where the denominator is a function of theta 2, whereas the second quantity f theta 2 theta 3 can be written in a way where the numerator is a function of theta 2. Okay, have you understood this? You confirm, I mean, like you are not only one or two of you are like responding,
Yes,
others
sir.
are always silent. You should also like sometimes tell if you have like some problem or so on. So why we are writing them as a as a division of these quantities? Because theta 2 is here, is there on the right hand side, but not on the left hand side. Therefore, we have to assume that theta 2 is there here, but it gets cancelled after multiplication. And it will get cancelled after multiplication of two terms when in one of the terms theta 2 will be a function of a function in the denominator, and in the other term theta 2 will be a function of the numerator. Okay. Okay. So now if you multiply, okay, so this is considered to be equation 6 and this is considered to be equation 7. 6 and 8, really? Where is equation 7 then? Okay, it should be equation 7. So, okay, there are some printing mistakes. It is equation 7. Okay, it is not 8. It was given to be 8. I don't know, printing mistake. Now, if you multiply these with these, so f theta 1 theta 2 multiplied by f theta 2 theta 3. So these two terms will get cancelled and we will be left with phi. So phi theta 1 is also a function of temperature, because for our convenience we assume that phi theta 1 divided by phi theta 3, and f theta 1 theta 2 f theta 2 theta 3, this one from equation 5, it is nothing but f theta 1 theta 3, or after multiplication, so phi theta 1, phi a function of theta 1 divided by phi a function of theta 3, or f equal to theta 1 theta 3. How f equal to theta 1 theta 3? If you see this multiplication from equation 5, this multiplication, it is the same, this one is same as this one, therefore this one we can write here, and a capital F theta as a function of theta 1 and theta 3 will be nothing but phi theta 1 divided by phi theta 3. Okay, so you understood up to this? Okay, I am removing the annotation here. Okay, now representing this phi theta by something tau, this symbol is tau, the temperature on the thermodynamic scale we get. So where is it? Q1 by Q2 is equal to tau 1 by tau 2. Okay. So, okay. So, what did we get? Q1 by Q2. Q1 by Q2 is F theta 1 theta 2. Okay. So, let me write. So, So Q1 by Q2, what was it? Q1 by Q2 was found to be a function of f theta 1 theta 2. Okay, this is a bracket. Okay, so writing with a mouse is really difficult. You trust me. Therefore, f theta 1 theta 2 is what? F theta 1 theta 2 is, again, we assume that it is like a division of two functions, because no, here theta 2 is not there, but there is theta 2. So that is why we have to express this quantity equal to, so this one equal to phi. You write this phi theta 1 by phi theta 2. Uh, Phi theta 1. Uh, no, what did I write? Q, not Q. Okay, let me do this. It's not Q. It is, in fact, phi. Phi. Yes. Divided by phi. Phi. Phi theta 2. Okay. But now, okay, so you have understood this Q1 by Q2 is phi theta 1 by phi theta 2. But now here we are replacing this phi theta with a quantity tau. Okay, so phi theta is tau. If phi theta is tau, then phi theta 1 can be written as, so here from here to here, tau 1 divided by tau 2. Okay, so Q1 by Q2 is nothing but tau 1 by tau 2. Okay, so tau 1 is again a function of temperature theta 1, and tau 2 is again a function of temperature theta 2. Okay. Okay, so okay, this is equation 9. Okay, so what is written next? Let us read. The thermodynamic or Kelvin scale of temperature is that scale on which any two temperatures are in the same ratio as the quantities of heat absorbed and rejected by Carnot's reversible heat engine operating between these two temperatures. Okay, so okay, so if you go back to the again concepts of Carnot's engine, or a normal heat engine, so whatever be the temperatures there of the source and the sink, if you take the ratio of the temperatures of the source and the sink, then the ratio of the, no, sorry, the ratio of the heat taken from the source and heat absorbed, okay, and heat rejected, okay, Q1 and Q2. Okay, we are talking about Q1 and Q2. Okay, uh, heat engine operating between, so with these two temperature at the same ratio. Okay, so the ratio of the heats absorbed and heat rejected, it will be nothing but the ratio at which these two heats are related to. Okay, these two heat quantities Q1 and Q2 are related to. Is that scale on which two temperatures are in the same ratio? Two temperatures, these tau 1 and tau 2 are the temperatures, they are in the same ratio as the quantity of heat absorbed heat operating between these two temperatures. So you understood this? So this is nothing but another form of Carnot's theorem. Okay, in Carnot's theorem also we also learned what we learned. So Q1 by Q2 is equal to T1 over T2. But here we have done some more like treatments and derivations to exactly find in what form the function should be. They are actually the parts of numerators and denominators. And this scale of temperature, which is represented by this tau 1 and tau 2. So that is actually the thermodynamic scale of temperature. Okay, then let us see what is written next. So I hope you have understood up to equation 9. Okay, and it is the same. The whatever the statement is given here, this is the same statement as this. Okay, so you don't have to remember this as it is written here. Like this highlighted part, you don't have to remember the statement. If you can derive up to this equation, then it is easy to write this statement. Okay. Okay, if you things we will learn from here on. Okay, so like why we do not get negative temperature, etc. Why temperature is never negative? No? Negative means in absolute scale. We can have the negative of degrees Celsius, but in absolute scale, temperature is never negative. So anyway, so let us first go through this and then we go to the other part. So a zero of absolute or thermodynamic scale. No? The efficiency of Carnot reversible heat engine, we all know this by now very well. Okay. On thermodynamic scale, this is what we have just learned. What is on thermodynamic scale? Q1 by Q2 is tau 1 by tau 2, or in other words, Q2 by Q1 is equal to tau 2 divided by tau 1. Okay. Okay. Or since Q2 by Q1 is equal to tau 2 by tau 1, therefore what is the efficiency? Efficiency eta, this quantity is the efficiency. Q2 by Q1 is tau 2 by tau 1, therefore eta is equal to 1 minus tau 2 by tau 1. Okay. Therefore, suppose tau equal to 0 Kelvin. Suppose tau 2, not tau 1, both are actually tau quantities. Let me try annotating. Suppose tau 2, this temperature is 0. Okay. In that case, what will get efficiency is equal to 1. Okay. The tau 2 equal to 0. In that case, the efficiency will be, if this is equal to 0, efficiency will be 1. Substituting tau equal to 1 in equation 10, we get Q2 equal to 0. Okay, I forgot what is equation 10, but I very well remember what is the relationship between okay, Q2, what is the relationship between Q1 and Q2? Okay, so if tau 2 equal to 0, then efficiency is equal to 1. Okay, now if efficiency is 1, if this quantity is 1, so 1 equal to 1 minus Q2 over Q1. So 1 gets cancelled 0. So Q2 by Q1 equal to 0. Okay, so Q2 by Q1 is equal to 0, or in other words, Q2 equal to 0. Okay, because tau equal to 1 minus q2 by not tau, sorry, eta, it is called eta is equal to 1 minus q2 by q1 if eta is equal to 1 as given here, as we obtained here. So q2 will be 0. Now if q2 equals to, okay, q2 equal to 0 is what you got. Okay, the same thing. Thus, zero or absolute or thermodynamic scale is defined as the temperature of the sink at which reversible heat engine undergoing Carnot cycle rejects no heat to it. Okay, so Carnot cycle. Okay, let me quickly draw the cycle. This is the source. This is the sink. This is the working substance doing some work. W. Okay, work we are not considering here. Here we are directly considering uh, T1 and T2. This one maintain that, suppose Q2. Okay, so here it is taken to be tau, not T exactly. Tau. Tau is written a bit differently than T. Q2 and temperature is tau 2. Okay. So what is the when Q2 equal to 0, that is the zero of absolute or thermodynamic scale. Okay, zero of absolute or thermodynamic scale. If we call what is the zero of thermodynamic scale, oh sorry, what is the zero of the absolute scale, then what you will say, define as the temperature of the sink. It is the, because tau 2, what is tau 2? Tau 2, where we get tau 2 equal to 0, that means if tau 2 equal to 0, Q2 will also be equal to 0. Okay, then how we can combine both? The zero of absolute or thermodynamic scale, okay, zero of absolute or thermodynamic scale, we are talking about this, is the temperature, is defined as the temperature of the sink. Okay, tau 2, okay, tau 2 is always the temperature related to the sink. This is the sink. Okay, this is the source as let me write S I N K, and this is source SOURCE. Okay, this is the source, this is the sink. Okay, so at if T2 equal to 0, Q2 is 0. So again I am reading the statement. The zero of absolute or thermodynamic scale is defined as that temperature of the sink. Okay, sink temperature, this is the zero or thermodynamic, this is the zero of absolute or thermodynamic scale at a sink, at which the reversible heat engine undergoing Carnot cycle rejects no heat to it. At which the reversible heat engine, this is the reversible heat engine. Okay, reversible heat engine means I have to write that heat is being taken, this heat is Q1, and some heat is being rejected, the rejected heat being Q2. The temperature of the sink at which the reversible heat engine undergoing Carnot cycle rejects no heat to it, Q2. Okay, you understood or not the definition? So zero of absolute thermodynamic scale is that temperature, I mean the tau 2 temperature has to be 0, that temperature of the sink, it is the temperature of the sink. Okay, for which the heat engine will the reversible heat engine undergoing Carnot cycle will reject zero heat to it. Zero heat means if tau 2 equal to 0, Q2 is equal to 0. Okay, that is the zero of absolute or thermodynamic scale. Okay, I hope you have understood this. Then okay, I will write everything in the note. My note is half ready actually. Okay, so why negative temperature is not possible? This may also be a short question, or yeah, so you should know it. Okay, the zero, this topic. Okay, the zero of absolute or thermodynamic scale is that temperature at which the reversible heat engine undergoing Carnot cycle rejects no heat to the sink. Okay, this is the same definition written here. A negative temperature on this scale means that heat engine extracts heat from the sink at a lower temperature and give it back to the source, which is against the second law of thermodynamics. Okay, now if somebody asks you like why we do not have okay, why is it coming? Okay, let me just go to annotation. Can I do highlight here? Is this a highlighter? No, no, not highlighter. Anyway, scale is the best. Sorry, pencil is the best option. Yeah. So you see, if temperature has to be 0, or if Q2 has to be 0, the 0 of the absolute thermal is there. Okay, this definition we have learned, that is a negative temperature means that on this scale means that heat engine extracts heat from the sink. Okay, at a lower temperature and give it back to the source at a higher temperature. Okay, so the heat engine is working like this. It is taking a heat Q1, okay, doing some work in the middle and rejecting a quantity of heat Q2 to the sink. Okay, and if temperature tau 2, okay, tau 2 can be 0 at best. Okay, if tau 2 is some negative quantity. Negative quantity means you have to how is it written? On the scheme, it have to extract heat from the sink. Well, suppose the sink is at a temperature of tau 2, no? That means you have to take out heat from the sink, which is not possible according to the second law of thermodynamics. I mean, for a spontaneous process, it is not possible. Like in refrigerator, yesterday we have learned in refrigerator, it is possible to cool down a body at a lower temperature, but it is not possible to, but in naturally or spontaneously, it is not possible to cool down a body at lower temperature because heat always flows from a body at higher temperature to a body at a lower temperature. Okay, so this is also the case. I mean, to get a negative quantity means 0, no, tau 2 can at best be 0, but if you want to get negative quantity, you have to do work, you have to take out heat, then only then it will become less than 0. Okay, if it is less than 0, it is not possible. Okay, so tau 2 cannot be a negative quantity. Okay, otherwise spontaneously this is not possible unless you do work by some external agency. It is not possible to take out heat from the sink at lower temperature because the minimum value tau 2 can have is equal to 0. But if you are taking out heat, that means I mean tau 2 can be negative only if you can take out heat from the sink, which is not possible, and it violates the very concept of second law of thermodynamics. Okay, so I hope you understood this. Negative temperature is why is negative temperature not possible. Okay, it will be included in your note. Okay, anyway, that's all for today. I am stopping the share because we will have to finish the class in a few minutes. Okay, so 8 of you are present.
Sir,
Yeah, you have a question?
thank you, sir.
Okay. So you want to leave the class? Anyway, so I
Right.
think, yeah, I think we are almost going to finish the class. So, yeah. And I think tomorrow we have two classes, okay? One from morning 9. Tomorrow is Thursday, right? Thursday. One from morning 9 and the other from afternoon
Yes, sir.
1. Yeah, one from morning 9, afternoon 1. So in tomorrow, let us see. We may discuss some numerical problems based on this chapter, okay? And then only next week we will go to this thing, unit 2, entropy, etc. Okay. Okay. Anyway, so I am finishing today.